it's really a pleasure that Danielle agreed to join us today. As I told her, she was one of the two top choices that we wanted to bring. Unfortunately, we got both of them. We got May Griffith and we got Danielle Levac. I'll do a very brief intro, and then she can maybe say a little bit more about her career path. But basically, she's a physiotherapist. She did her degree in University of Ottawa, then did her master's and PhD at McMaster, then came back to Ottawa to do a postdoc, and now she's a professor here at the University of Montreal. So a very Canadian researcher.
That's right.
And for everything else, I'll leave it to Danielle. Welcome, and looking forward to your presentation.
Thank you so much. Great, really happy to be here. Can everybody hear me? Okay, just let me know if not, okay? So I'm happy to be here today and then next week. I really look forward to hearing your presentations and your talks next week. My postdoctoral fellow, Sam Marie, who's an engineer, will join us next week. So I think he'll really enjoy being part of that. For the presentation today, I have a lot of slides, a lot of information. We'll see how much we get through. Otherwise, I'm happy to make the presentation available to you guys, and I welcome questions or comments at any point. So I thought we'd talk a little bit about me. So how did I get to this point? What is the reasons why I chose VR and technologies as a research path, as a career path? Make sure we're on the same page about what virtual reality is and what it isn't. There's a whole continuum of definitions and technologies. And then, how does it relate to rehabilitation? And I'm coming from the perspective that you guys might not know a lot about rehabilitation or physiotherapy. Maybe you're yourselves or your family members have been involved in physio or some type of rehab in the past. But we will do a little bit of an overview of what might be the relevance, how does it actually insert itself into therapy? And then we'll talk about what some of the research projects that I'm doing and some of the things that are coming down the path in this field. And so one thing that really makes me happy to be here is that I've always worked very closely with engineers. I mean, they're essential to what I do. I don't have the programming skills. I don't have the development skills. And so I've always worked in interdisciplinary teams in this area. We as therapists will have ideas. We know what works best for our patients, what are the functional goals we want to achieve. And then working with engineers and game developers and programmers, they can create a game or an application that will go and get those targets. And together, it just really works best. And that's where we've had the most success. I'm going to briefly say, too, I don't have any slides about it today, but remind me next week with Abulfaz Mohabi, who's a professor here in mechanical engineering. We have a club called Club Readapt Techno. And the purpose of this club is actually to bring rehab, physio, OT, and engineering students together. And we solve real world tech problems for kids with disabilities. So we're adapting a scooter for a child who has balance issues and needs a wider base of support. We're making a device that helps a child who uses a wheelchair transfer from her wheelchair to other services. So if being involved in this club appeals to you, don't hesitate to let me know. The meetings are here every Thursday night at 6 o'clock. All right. So as Nicolas said, I'm a physiotherapist by background, and I worked always with kids, but I always knew that some of the words are going to be in French. It's kind of a franglais presentation. So I always knew that I wanted to go back to school and do research. And so I did that at McMaster University. And I'll tell you about what I did in my master's and my PhD. Then I went to do a postdoc because in order to become a professor or have a career in academia, postdoc is necessary, and it's a really great experience. I actually did have a little bit of a US experience. So I was at Northeastern University in Boston for the first 6 years of my career as an assistant professor. And then it's only been about 2.5 years now that I've been back in Montreal at the University of Montreal, where I am a professor in the Faculty of Health Sciences and a researcher at CHU Saint-Justin, which is the children's hospital here. And I'll tell you more about that specific involvement in a couple slides. So when I was doing my PhD, I did it at Holland Bloorview Kids Rehab Hospital, which is Canada's largest pediatric rehabilitation hospital in Toronto. I had worked for a number of years at that point with kids, as I said, and it was around that time, I'll date myself, it was around 2006, 2007 that the Wii first came out. And it's so old school now. I'm sure you guys, I don't even know if you remember growing up using it, right? But it was kind of really a revelation at the time, because here finally we had a game that involved movement And we could use it in our rehab interventions to try to get kids to do things that they otherwise might not want to do or be interested in doing for a long enough time. Okay, so the Wii, as we know, has the controller, so you can play games using your arm, but it also has the Wii Fit balance board for, you know, weight shifting, postural control, those kinds of things that appeal to physiotherapists. But as anyone who's played it knows, it's also quite easy to cheat on it, right? You don't need these large movements to play tennis on the Wii. You could just get away with tiny little movements. So in the PhD, what we were looking at was, what is it about using the Wii that is relevant to physiotherapy? There's a picture of neurons connections there because we're really focused on neuroplasticity and motor learning. So briefly, neuroplasticity is anything that happens to your brain. Right now, listening to this, your brain is changing with this experience, right? And after a traumatic brain injury for kids, their brain is going to change, it's going to relearn. And if we don't offer them the right path, it's just going to relearn maybe movement strategies or patterns that maybe aren't optimal or ideal. It's the whole concept of learned non-use. So it may be someone in your family, unfortunately, maybe have had a stroke. So you understand that after a stroke, the brain is hurt and it needs to, the connections rebuild themselves. Well, we have to, in rehab, point the connections in the right way so that they're most functional possible. So the questions we were asking in the PhD was, what is it about using an interactive, engaging environment that might help this neuroplasticity, these brain reconnections? Is it the feedback the game gives? Is it how motivated the kids are? What are the active ingredients of this intervention? And why might it not work as well? Because if we think, for example, about a traumatic brain injury, kids have attention challenges, behavioral challenges, and these are kids who had a normal developmental path up to that point. So they may be really challenged or dissatisfied with their performance on the game, and that could induce some emotional consequences as well. So the PhD was really exploring the use of this one particular active video game in rehabilitation. When I got to Northeastern, which is a private university in Boston, I continued along this same line of thinking. And the research program that I had there and that I continue today really has three kind of global aims. So the first is to continue this exploration of what are the mechanisms of motor learning. So motor learning is when we learn or we relearn a new task. What is it about a virtual environment that supports motor learning? And how does practice in the virtual environment transfer to the real world? So transfer is huge in learning, right? So you guys in your classes, yes, you're learning skills, but we don't want it to stop there. We don't want it to end when you leave the classroom. We want you to be able to take those skills and integrate them into your real world knowledge, to build on what you've learned before, to make connections. And that same thing happens in rehabilitation. Okay, we don't want the child to just practice going from sitting to standing on a chair with no arms, but we want that to transfer to a chair with arms, a chair of a different height, a chair in a busy environment. And so that's some of the questions that we're interested in. How does it transfer? If you play a game, how does that transfer to getting better in your real life? We want to obviously develop and test new interventions. So we want to be part of creating evidence in the field. Why should these interventions be used, and with whom, and how long, and those types of interesting questions about intensity and frequency. And importantly, we want to work with therapists for knowledge transfer. And so that's really, really important in healthcare. I can develop all the cool games that I want and all the great evidence that I want, but if it's never translated into clinical practice, it'll never get used. And I think we have that problem a lot with technologies, is that we try to say, there's this new technology, why don't you go and use it? And therapists and doctors need a little bit more support or resources to know how to use it effectively. And so that's a big part of our research program, is making sure that we support the people who are actually going to use these tools in clinical practice. So a couple of pictures from the lab at Northeastern. We did our work not only in our lab, but at children's hospitals, and then often in the community as well. So some of the pictures you'll see are from what's called the Tech Kitchen at the Boston Children's Museum. And that was a place where we went to try out our games, try out our innovations with typically developing kids. So typically in research, before we do something with a clinical population, we want to make sure that it works, and we want to, iron out any problems. And we'll do that often with a population who doesn't have any impairments, typically developing kids. And so often we would go, and whether it was a VR game that we had developed, we also were looking at robots. So building really, I don't know, you can really see it, but a really low-tech robot that responds to a child's hand movement. So we would test those. And so these are just some ideas of the research that we undertook while I was in Boston. So as I said, I'm really happy to now be back in Montreal. In addition to my teaching and professor duties at the University of Montreal, I'm a researcher at the CHU Saint-Justin. Not only is my research program there, but I head one of the 6 axes of at the research center. Our research is divided into 6 themes. And so currently I'm leading the musculoskeletal health, rehabilitation, and medical technologies theme, which involves about 60 researchers. The CHU Saint-Justin, if you don't know, you're probably familiar with the building that's close to here, the main hospital on Côte Sainte-Catherine. But where I'm based and where all of our research takes place is at the Marie-Enfant Rehabilitation Center, which is in the east of Montreal, at about Bélanger and 40th Avenue. And it's in this building here where my research takes place. This building is the Technopole in pediatric rehabilitation, and it's attached to the Marie-Enfant Rehab Center, which is sort of in the background here. And I'll tell you about the Technopole, why it's important. So I mentioned here the axe that I lead. And so here we have a couple of pictures from the different research programs in this axe. As I said, about 60 researchers. A lot of it is based at CHU Saint-Justin, looking at diagnostic technologies, prognostics, therapeutic approaches. So you may be familiar with the work of Carl-Éric Aubin. And so he's quite a leading figure in this field, developing smart corsets for children and adolescents with scoliosis that gives feedback about their wearing duration and other biomechanical properties. So a great focus of this axe is really in orthopedics, spinal deformities, musculoskeletal diseases, and that's based at the CHU. And where we're at the Technopole at Marie-Enfant is everything more related to pediatric rehabilitation. There's also a sports medicine volet axe, and we're looking at preventing reoccurrence of injuries in teenage athletes and everything to do with concussion, which is a big problem, obviously, for athletes of all ages, and certainly for children and adolescents. So back to the Technopole, this is the building. It's very recent. It was built only in 2019, very quickly, actually, within about 18 months, and a huge investment of funds from the provincial government. And the idea behind the Technopole is that being associated, that's literally linked to the rehab center, that you would bring research and clinicians, clinical service together in the service of evaluating and using new integrated technologies. It's called the Technopole for a reason, in pediatric rehabilitation. So a lot of these words are in French, but just to show you, here we've got a bunch of different technologies. I think I've got, no. So we've got the picture that you're seeing here, and I'll show you the video, is a virtual reality gait training environment with a treadmill and an integrated motion capture system, and that's the Grail, and you'll see a video in a second. We've got another, the Locomat, which is another robotic gait training system. Lots of different assistive and augmented devices, wheelchair prescription, 3D printing, my research program in virtual reality, and a large gait lab in which we can look at the effects of our intervention on children's movement. My lab at the Technopole has a French name. I haven't come up with a great English name yet. And essentially technological innovations in pediatric rehab. So that's a bit where I'm situated. Now we'll focus a little bit more in on VR. All good so far? Excellent. So VR, just to be, VR, what is it? Like, that could be a whole lecture in itself, right? So I like to use this definition because it's vague enough that it kind of encompasses all sorts of different systems. So you can read it. I think it's pretty obvious, right? You guys would know it's an imagined environment. You're using your movement. So that's what's important to rehab, right? We want movement to be involved. Otherwise, if it's just a computer game with a mouse, maybe that's working cognitive skills, or maybe it's working, other types of skills. But in physical rehab for physiotherapy, we want the child or the person to need to use their body to interact with the game. Probably when we think of VR, the best true definition of it is anything that's immersive VR. So where we are visually, sometimes auditorially as well, immersed in the virtual environment, right? And then that virtual environment changes. As we look around, it's going to change in accordance with our head movements. Okay, so, and the vision that we see is 3D. So if I see an object in VR, it's going to be, the virtual object is at approximately the same distance that it would be in real life. So those are the important things about what we call immersive VR, which some of you may be familiar with. How many people have a VR headset at home or have tried one? Yeah, that's it. So in immersive VR, obviously, again, with so many different kinds, right? So all the way from the Google Cardboard, it's immersive. But no way of interacting with the environment, right? All you're doing is a visual environment, but you're not able to use your hands or movements to interact. One important mechanistic definition is where the movement tracking is coming from. Is it coming from the headset, like the Meta, or used to be Oculus Quest, or is it coming from cameras or sensors outside of the headset, like the HTC Vive that we use often in our research? And so obviously this is sometimes what we also call, there is a little bit of an illustration here of a cord between the computer, but this is unencumbered. So we don't need a computer, like all of the simulations, the computer itself is in the headset. And here we need to be either wirelessly or not tethered to a really high powered VR PC in order to run our simulations. So lots of different headsets, continually new ones coming out, and we'll talk about that as an advantage and as a challenge for researchers and clinicians. And right now, it's not important that you see the details here, two systems here that were created specifically for kids. We'll talk about some of the challenges of using immersive VR with kids in a second. Then we have the semi-immersive, non-immersive, and whether people think it's VR or not is a huge question, right? Virtual environments, we'll say. So here obviously is, no matter the size of the screen, right, you're still in your physical environment. If immersion is a physical property related to visual sense, then you're less immersed. If immersion, you think of it more as a psychological property, like you can be immersed in anything. We have to immerse in books. You don't need a screen to be immersed in something, right? So I like to think of immersion as a property of the environment. And so here, obviously, we're using movements, and big screens can be really, this is my lab at Northeastern, really immersive. But again, the size of the screen doesn't matter. The idea is that obviously you're viewing it on a screen in 2D, right? The objects are not coming out at you in 3D. So here we talked about the Grail, just to show you what that looks like. We use the Grail a lot in rehabilitation. So here you're seeing a game that is tracked. The interaction with the game, there are motion capture markers on the device that he's holding, and that's controlling what you're seeing happen on the screen. And he's also walking on the treadmill. You can see that the treadmill is also moving in a number of different directions. That is not, in this particular example, changing anything on the screen, but most other games, you're walking and the screen is moving, like you're walking through the environment, okay? And so semi-immersive, non-immersive, I mean, standing in front of it is quite a big screen, but you're not fully visually immersed in that environment. This is one example of the types. We have a research program looking at using this intervention in pediatric rehabilitation. So what about video games? So far, I started off talking about the Wii, you know, if you look at publications, a lot of them will call the Wii virtual reality, but is it? So a video game, an active video game is anything that is controlled by body movements, right? Versus a passive game might be more your controller game. And, you know, again, here we have a lot of different examples, right? So Wii games are commercially, they were not designed for rehabilitation. They were designed for typically developing healthy adults, maybe adults in need of more physical activity. Then we have serious games. So we have like a use function of some sort, whether it be learning to drive your power wheelchair, exergaming, any type of learning to be a physician, any types of skills. If we add serious to it, it means it has a function. And then games for health would be this category of like exergaming that I think most of these devices. So we have the Wii here. This is an old device that I worked on during my postdoc that is no longer available, but you see this, it actually puts this is you into the virtual environment. And so you see yourself reflected mirror wise in there. They actually sold their technology to Microsoft, and that was the basis of the Kinect. Then we have the Kinect here that you can't see behind this person who is interacting with the game using the sensor that's picking up their movements. So we'd also be remiss, and I know the font is small here, sorry, not to talk about augmented and mixed reality, right? Because I think really realistically, this is where it can have the most benefits for rehabilitation, because there are a lot of disadvantages to immersive VR, especially for a child. Like if they're in there, that's all they see. How can I interact with the child? Augmented and mixed is beneficial because I'm still in the child's environment, but we're adding these extra elements. So augmentation is essentially we're just overlaying, right? So Pokemon Go. But mixed reality is where physical objects can interact with digital objects. So we can have, for example, a virtual ball, and it's recognizing, the headset is recognizing that the table is there, and the virtual object is interacting with the real object. Okay, so that's a bit of the definition between both of those. And again, though, both of those are not fully immersive because you are still in your real environment. Really briefly, some of these factors are important for trying to differentiate. So how do you view it? We'll talk about game design. How can you measure the effects? Fidelity means to what extent is the virtual environment accurately mimicking the real world environment? And sometimes you want that. If your job is, if you want your virtual environment to be as realistic as possible because you want to practice real world skills, well, then it needs to be as representative as possible. But sometimes you just want it to not be. You want it to be just totally a different environment because that's what's going to get people to adhere to their rehab and be motivated. Immersion and presence, really briefly, presence for me is more the psychological aspect. How convinced am I that the environment that I'm in is quote unquote real? Like how much do I forget about the other environment when I'm in? And you can be present in a non-immersive virtual environment, but it is true that presence is obviously higher in an immersive VR, right? And then how do you interact? So are you holding a controller? We use a lot of gloves, haptic gloves in our work. So you get a little bit of feedback when you're touching virtual objects. All of these things are important to try to say, are you on the more VR or the more video game end of the continuum? This isn't what we're going to talk about today, but you probably have heard about all these applications for VR and AR in healthcare in general, right? So a lot, and we'll talk a bit about telerehabilitation, the idea of being able to follow what patients are doing at home and provide games and interventions that they can do at home. And then a whole lot in training. Not just medical, but any type of a health professional training. So this idea that we can mimic with safety and you can make errors, right, without consequences in a virtual reality environment. Huge applications with respect to pain management, not just, so one big one is obviously the opioid crisis. So instead of prescribing painkillers to people, can we have them go through meditation or immersive experiences as in VR that would distract them or be a pain relief device? And a lot in kids undergoing chemotherapy, burns, in terms of avoidance of opioids, pharmacologics, and use of VR instead. And then certainly in the US military, and any military applications, treatment for cognitive phobias or post-traumatic stress disorder by safely re-immersing the person in that environment and having them re-experience that situation, or having them experience a situation in which their fear is present, but they know objectively they're safe. Okay. So we'll talk now a little bit more about kids, because that's always been my research focus. That's where I work. That's my understanding of rehab as a physiotherapist. And so some of these words might not make a lot of sense to you, but essentially in pediatric rehab, what we want to do is take the consideration of the child as a whole person, okay? So we're not focused on their impairments, what's wrong with them, quote unquote. We're not trying to solve what's wrong with them. Sometimes we are, because sometimes we can solve what's wrong with them. But a child with a long-term developmental disability is not going to be fixed. So what we need to do is understand, okay, what is the role of the environment and our interventions? How can we focus on the child within the context and say, well, maybe the problem isn't that the child uses a wheelchair. The problem is that there's no ramp for the child to access the library. So we're looking at participation and activity, not impairments necessarily. That's to say, not to say we don't focus on impairments. Of course we do when necessary. But in the past, the medical model has traditionally viewed people with disabilities, the problem being them, right? Rather than the problem being that the environment isn't really set up for their needs. And we mentioned a little bit already, this neuroplasticity and motor learning. So we know in rehab, it's not good enough just to get the child to repeat some meaningless action over and over. We need that to be in an interesting environment. We need to be a task that is important to the child. We need variability. We need lots of engaging stuff, and we need to involve the child actively in the intervention. We're not just going to bend their elbow, but we're going to get them to bend their elbow and get them to be involved. Okay. So obviously I could talk a lot more about that, but I wanted you guys to know that that's the context that we're coming from. And now we have to think, okay, so why would, in that context, why would we use VR? So we can think about some reasons. We want children to be actively involved in their interventions. And we also know that from a motor learning, a brain changes perspective, you have to do stuff a lot. You have to do a lot of repetitions. And sometimes that can be a problem, not just for adults after stroke who aren't getting the amount of therapy that they might need, but for kids who aren't interested, motivated, or wanting to do the repetitions that are required for those changes in the brain. So if we can just basically use a more engaging or motivating intervention, maybe they will have a higher adherence to the dosage of therapy that we want. VR could also be a great environment to learn new skills and practice new skills. It can also be a nice environment to practice higher risk skills that maybe you're not ready to do in the real world yet. Crossing the street or any type of occupational training, power wheelchair training, a lot of that is done in VR. Because we can, to a certain extent, depending on the hardware, mimic the real world environment. Of course, we'll never, with haptic gloves, it comes close, but there's nothing stopping me from squeezing through the bottle in VR, right? So we'll never fully mimic the touch, the feedback we get from touching objects in virtual reality, but we can come close. Maybe the interventions aren't effective and we're interested in VR as a more effective intervention. And maybe we actually just want to equalize the playing field for kids with disabilities. And so maybe we can have a controller or some option where they're able to participate in the way that they can with the range of motion that they have, or even the head motions that they have, and they're able to participate in the same game as someone without a disability. So those are just some reasons why we might integrate. In more detail, and I said all these reasons already. So motor learning, maybe we can have less, from a cost perspective, maybe the therapist can be less involved, and we can have a technician, or we can follow that person at home. Motivation for repetition of exercise. I didn't talk too much about it, but maybe it's simply this exergaming element. So the idea of staying fit or having access to exercise opportunities that you might not otherwise. So I'm thinking about people in isolation in the hospital, for example, anything where you are physically unable to exercise in other means. We talked about real world skill training because the safety and ecological validity just means the way that a virtual environment might mimic the real environment. And a lot of stuff we can do is in assessing, diagnosing, monitoring, because we're really able to have specific testing conditions so we can really narrow in on a particular situation, and we can get a lot of interesting data at one time. So for example, during my postdoc, we looked at the University of Ottawa hockey team. We had them come into our virtual environment, kind of like the Grail that you saw, but it was a bigger one, and the platform moved in all 6 degrees of freedom. So before the season started, and then after each concussion, and we could see that even though they were doing well on the standard balance tests that we would do in the real world, stand on one leg, eyes closed, this really high-tech environment coupled with the visual feedback on the screen really allowed us to see more specifically that these concussions were having an impact on a lot of different functions that otherwise we wouldn't be able to assess. So neuroplasticity, I already talked about it. It's just experience. And the damaged brain is going to reorganize. And it can be in a good way, helpful way, or ultimately a long-term harmful way. So after a stroke, if someone is consistently compensating using a pattern that might break down joints or be damaging musculoskeletally, that is a harmful compensation strategy. And so what we're trying to do is promote how the brain reorganizes functionally in more helpful ways. We talked about vocational training because of this safety. And in pediatrics, again, it could be spatial navigation. So some kids have a hard time planning out where they're going. And so if we replicate a particular course in VR, they can make decisions about where they're going, how close they're gonna come to different obstacles. Pain management and participation, talked about those things. So if we want to think about, okay, it sounds really great. Why isn't everyone doing it? It's because of all of these obstacles. Some of these things are really expensive. The Grail is never going to be in your local physical therapy clinic. A lot of these games that were designed for the general public don't really align with physical therapy needs or objectives, right? They're either too hard or they're too easy. Some therapists don't have assistance with using it or installing it or fixing it if something breaks, which we know it always does. Some centers, including, I'll have to say, the Technopole, focus on buying the very cool things, but not on training their therapists how to use them or having a budget for fixing them. And oftentimes, including some of the equipment that we have at the Technopole, some of the robotics in particular, young children can't use it because they're too small for the device. So those are some obstacles to integration that we're trying to tackle in our research. So one thing that's interesting, many of you might be gamers, is that if you think about VR, unless we're talking about a job training environment where you want to pick up a box and put it on another shelf, usually it's a game. And particularly with kids, usually it's a game as well. So if we want, and there are known principles about what makes a game a good game. Okay, and we have to follow those principles if we want the game not only to be therapeutically relevant, so it's asking for the right movement that I want the child to do, but that the child's going to do it, right, and be interested in doing it. And so it's kind of at this intersection of all of these motor learning principles. How much feedback do we give? You know, how many repetitions? These principles of game design that you would note are important to not just the game that you play on your smartphone, but any video game that you're interested in. And then what do we know about, you know, what happens when people are motivated and engaged? If you're interested in what I'm saying right now, you're going to retain a lot more of this information than someone who is not interested or engaged. And so it's right at that intersection that we need to be working when we're designing games for rehabilitation. And why do we care so much about motivation and engagement? So motivation is kind of goal-oriented behavior. Engagement is more your experience. Are you or are you not engaged in what you're doing? Very briefly. So if I am engaged or motivated, the indirect pathway, like the non-physiological pathway, is that I'll just do more of it, right? I'll study more, I'll do more repetitions. I will better adhere to what I have to do. And so through that mechanism, I'm engaged, I'll do it more often. Maybe then I'll have learning better and it'll be more encoded in my memory. But there's also a more direct pathway, which is what happens in the brain when we're motivated. Everything to do with dopamine, okay? So this idea of the chemicals that are involved when we're more motivated, the effects that those have on memory consolidation, the direct effects that those have on learning. So we could go this way, that's fine, but ideally we're going both ways when we're trying to design a virtual reality therapy game. One example, this is a research project that we have going right now, where we developed a new game, an XR game, because it uses the Kinect sensor. The latest Kinect sensor is called the Kinect Azure. And the idea is that it would provide an at-home option for children with spinal muscular atrophy. I think it's quite a long video, so we'll just... So here we have one of the study therapists showing the movements that are required and that are picked up by the sensor. And in this instance, it's calibrating to her abilities. So if I was able to go a little bit less far, it would calibrate and I could play the game according to my abilities. So what's interesting about this project is two things. First is that the game, we're following some game design principles. It has a story. So as you progress, the story gets more complex. You have more challenges, and there are rewards that you earn at each level. They're extrinsic rewards, you know, points, but they're the same type of rewards that in Fortnite, et cetera, any other game that you're playing that makes you want to keep going. The second thing that is interesting about this game, you may not know this population. So this was previously, prior to the last 5 or 6 years, a terminal illness for young children because of dystrophy, the muscles, primarily cause of death is respiratory muscle atrophy. But the entire landscape of this disease has changed in the last few years with new drugs that stop the disease process. So now we have new children who are being born, and children, no matter what their level of progression was, oftentimes the life expectancy was usually 7 or 8 years, who now we're not going to be able to recover, we can't necessarily regain lost function, but we can stabilize and maybe strengthen a little bit. We don't know because it's the first time that we're able to provide rehabilitation for this population. So this is the first study where, and these children have a lot of medical appointments. And so rather than coming into the clinic, some of the advantages of telerehab, obviously, is that you can do it at home. Okay, so wanted to give you an example of one way in which what we've been talking about so far is currently being studied with a clinical population. Let's go back to immersive VR for a second. So lots of advantages with immersive VR. More immersion. Does it lead to more engagement? Am I more engaged if I'm in a visual? We need to study that and find out. Embodiment. So this idea of I may have my own physical limitations, but in the virtual world, I can do things that I normally wouldn't because we could enhance. So a movement that's like this in real life, I could magnify it in VR and it could be a large movement. That's just one example. You can see how that would be interesting for a child who lives with physical limitations. Do we have more natural movements in 3D than we would if we're looking at a screen, reaching for objects on a screen? And we can simulate the real world. However, none of this thus far has been designed for kids. A lot of what you know, and if I'm in a VR headset, I am automatically no longer with you in this environment, even though I'm physically present with you in the environment. I am isolated. Lots of costs, the safety issue, you know, we can't have kids running around with headsets on. Some challenges with side effects, and then more, you know, still, but pandemic era, certainly we have the same headset that lots of people are using. Some of the potential side effects that we have to watch out for are related to vision, certainly, and anything related to people who might have photosensitive epileptic seizures. So we don't know a lot, particularly for kids, what might be the effects of having a screen so close to your eyes for so long. And so certainly right now in our research, we obviously try to adjust the interpupillary distance of the headset as close as possible, but none of them are designed for children. And then obviously have shorter playing times. I think let's get that. So one really interesting thing is there's actually a lot of work that's been done, because VR is used in education a lot too, right? To try to, you know, instead of going on a field trip, why not bring the field trip to the classroom? So we know that particularly in children, young kids are sometimes not able to dissociate between what they experience in the virtual environment and what is real. And we also know that they're very prone to, because they have such a presence in the environment, that we have to tread lightly, because they can really react to what's happening in that environment, right? So that could be good. We can really have them learn in those situations, but there's a huge potential for harm as well in using VR with young kids. So I think that's something that we really need to note, is how children are potentially more affected than adults in this regard to the time they spend in immersive environments. And, you know, it's related to the whole screen time discussion in children. So we'll go through into some more challenges now. And briefly, you know, I titled this talk, "When is VR Therapy?" And that's because VR isn't the therapy, right? The therapy is the therapist who is doing it, and it's one tool. And so I'll let you read this quote from a study we did a long time ago now. She's saying, it's great, but it's a tool like any other, and it's me as a therapist who is making the decisions about how to use it or not. This is a really interesting point from a very pivotal publication in the field. And it underlines the fact that, which tends to happen, right? We might just adopt it without really understanding how or why. And so what we need to understand is, like, with whom should we use it? And why might immersion be necessary? Why might 3D immersion help, or why might it not help? Rather than just saying we should always use immersive VR because it's the most interesting, coolest thing on the market right now. Another real world example of a study that we did using immersive VR is we wanted to understand to what extent could VR help us assess visual motor deficits. And so basically that's eye-hand coordination, okay? The extent to which I'm able to accurately plan visually and execute motorically a movement. And this is a problem that a lot of kids with cerebral palsy have. And so here's one example. So currently the way we assess this is paper and pencil. The goal is to replicate these two figures. And this is the replication. And it's not a motor issue. It's not because the child has no motor control, right? You know, this is a visual spatial issue. So we said, well, let's assess it in immersive VR using typical tests that we do, where we have the child look at a target while reaching, so we can see the visual, look and reach, and then just reach the opposite of whatever the first thing I said, 3 conditions. And we tried to do it in VR using haptic gloves where they got feedback. So here, even though he's in front of a screen, he's immersed in the VR environment. And we can see that some challenges, I think these videos will work. So we thought the kids would do really well in VR, but what we can see here sort of is that, yeah, sorry, that you don't really need the auditory there. She's trying, so she's got a target in front of her, this target. And because there's no feedback, whether have I touched the target or not, she's just going through the target, right? So we're not getting what we want because she's just trying to figure out, okay, how do I interact with this, yeah, it's just her vocalizing there. Then this other child, so we see we're getting frustrated. We want to touch this target, right? And so it's just one example of, we learned a lot about how kids use interactive VR, but maybe a little bit less immersive VR about how we can use it to assess visuospatial coordination. Some things that might be interesting to you and as potential engineers is this idea of replicating. So if we want to understand how do people interact with a task, can we model it in VR? Can VR be a testing environment? So here we have two situations. One is bouncing a ball on a racket, and one is throwing a ball. Two common thing, well, bouncing a ball maybe less, but throwing a ball, very, very common. And what we try to do in motor learning research is we need new tasks, because by the time, you know, kids are 12 or 13, basically there's no new motor task that they haven't done except maybe juggling. And so we're trying to say, okay, what could be a new task? So bouncing a ball is a fairly new task that we can study, so we can see how do they learn it. And so what we're trying to do here in VR, both 2D, so here we have a manipulandum that controls ball release, and then the same task in 3D, and then the same task in the real world with motion capture markers on the ball, the string, the target. You can see, okay, if we train in 3D or 2D, how much does that transfer to real world? And we do the same thing with the ball bounce task. Another example of how we can use VR to assess. So here we have the ball bounce task. So we're at difficulty level 1, and what the can anybody identify what is happening to this task that might make the difficulty level be 1? Play it again. What's happening with the ball? Is that a natural ball speed? No. So we've removed the effect of gravity on the ball. Okay, so we are effectively making the task easier by slowing down the ball. And in the game, we can then, we have difficulties 1 to 10, and 10, I don't have a video, but it's full. It's like bouncing a ping pong ball on a racket. Okay. Then here's a more of a game. It's not a task as such. Anyone who's played Beat Saber? So it's basically Beat Saber for rehab. This is on a really fast level. But yeah, that's super fast. So essentially you're holding the controllers and you want to touch and or avoid certain objects. You know, less of a task. The task in ball bounce is continuous bounces without the ball falling, and more of a game, but you're still tasked with moving. And so in Astro Surfer, which I'll show in a couple slides, we're able again to calibrate. So if I can do this, I'll play the game, and if I can do this, I can play the game. All right, just conscious of time, so we'll move forward a little bit. Yeah, perfect. 10, 20. Okay, so one question, if we think about real world, mimicking the real world in VR, is do people move in the same way in VR as they do in real life? Yeah, the jury is out, but tending towards no. Important differences, right? Are they moving well? Like, is what we call the kinematics of movement the same if I'm reaching for my virtual bottle versus for my real bottle? And so lots of studies have done the same task in the real world as well as in VR, because we can try to mimic it. And we know that there are some differences, both in the speed, the accuracy. Are those differences important? That's the question, right? It might be important if we're training the wrong thing. We don't want to do that. But it might not be important if it's largely the same. And again, this question of transfer, right? Because what's really important is that we know that how we learn things really matters, right? We tend to learn things in a specific context, and sometimes it's hard to apply them in another context. And so if we're learning in VR where we're not getting any feedback, where a lot of visual information is present, does that mean that we can use those skills in the real world? And so lots of research, interesting research on this question that needs to be answered. I didn't want to bore you with a lot of studies, so we're not going to do that, right? Does it work or not? The answer is yes and no and maybe, right? So is it better? Is it equivalent? For who? which systems, which games do they transfer? And then this idea of what I just mentioned, task specificity. So that's the fact that usually we learn what we practice and we don't learn what we don't practice. A huge challenge in the field is all of these different names and words. Okay, so if you try to do a PubMed search for virtual reality, then you will get the Wii, or you often may actually also get a computer game. Okay, and you will get a huge high scale immersive VR environment. You'll get it all. Okay, so we don't have a really good nomenclature, and that really complicates our ability to synthesize the knowledge in the field and my ability to speak to therapists about what VR is, because we each have different understandings of what that might be. This field has developed really rapidly, and this is just it ended in 2019, but this idea of the number of publications in the field, hugely growing. Because it's developed so rapidly, it's been really hard to kind of get a solid foundation. And so we're not able to kind of learn from what we've done in order to make different decisions in the future. So one thing that is challenging from learning from what we've done is this idea of the technology rapidly becoming obsolete. So the Wii is still the most used system in rehab, but its production stopped, and I should know this, but at least 10 years ago. And so we find it now on eBay or Facebook Marketplace. This system I mentioned sold, the IREX, they sold their patent to Microsoft. And then now what's in your latest iPhone, which I don't have, but the latest version of iPhone is 2 or 3 times more sophisticated and better than the Kinect is. So we often will use phones now for motion capture rather than the Kinect sensor. And actually the latest Kinect Azure is now out of production because of that fact. So once, these just some of these headlines, right? So if I'm trying to say to a therapist, please buy this system, yet the system will be obsolete, and that's the case for Meta, right? I've already I don't know how many Meta headsets I have, so many, because each year there's a new one. We're good so far. A couple more slides and we'll take a break. Okay. So I already showed you Astro Surfer, which is the video that we saw. It's Martin Lemay is my colleague who is working on developing it. And so you saw the video, and I mentioned the calibration. You don't really need to see the details here. The only thing that's important is that this is you can pick all sorts of different parameters, right, to personalize the game, which you can't do in Beat Saber. You can pick hard, easy, or extra hard. But so that's why when this becomes a rehabilitation game. The other thing that makes it a rehabilitation game is that we measure a lot of stuff, right? So we're able to measure the average distance, the success rate, the range of motion used, all those things that are important for a rehab. This is my lab at the Technotech. It's called, my lab at the Technopole, it's called the Technotech, which is obviously a play on bibliothèque. And so what it is, as you can see, a VR gaming room. This table can be moved. So this is a big empty space here for immersive VR play. And it is, it's in French, an offer of service to the rehab center where myself and my students, we consult with therapists. We're there when they use the games with the kids. So these guys are playing the Wii Switch, and this guy needed to work on bimanual integration. So he's using 2 hands to hold the racket in which the Nintendo Switch controller is in there. So we're helping them to integrate it. The room is available to them for use, and we have a whole research project about how well it's being used. And we'll also offer distance. So and by distance, what we mean is we can lend them equipment, but we also have an application. I know you cannot see there, it's not important. An application and a website that talks about the different games. The application is a decision-making algorithm. So if you answer certain questions, my kid is 7 with CP, wants to work on balance, it'll suggest some of the games that might be most applicable to that child. So we're doing a feasibility study now. These are a couple of kids who are using the room right now with 6, started with 6 therapists, and we're opening up the room in January with Audrey, my master's student, to study how many therapists are using it, how we can support them in the room. So here's one example of how we've used it so far. We run a summer camp at the rehab center that provides this therapy. And the basic thing to know about it is that we're trying to have kids with hemiplegia use both hands together and including both legs and postural control. And so half the kids in the camp spend 2 hours a day in the Technotech. And instead of doing the regular interventions, we target their goals using VR and video games. So you can't really see here, but Ibel is holding a soccer ball. It's a soccer game projected on the wall. And so when Xavier here is doing his soccer kicks, we can integrate the soccer ball into it. Here we have the Microsoft Adaptive Gaming Kit, which is only for Xbox One, unfortunately. But instead of using the controller, we have a number of different switches and then this whole pad here. So you can play doing this, right? Instead of the fine motor. And so this kid needed to work on prise digitale. And so instead of just doing that, picking up objects, he was able to use switches to do that. Integrating real world object. This is a rock climbing game that you can't see. So while rock climbing, he's grabbing onto an object, which isn't part of, you don't grab onto a stick in rock climbing, but at least you got that physical thing. And then we can't see, but we have two kids here competing against each other in the Nintendo Switch game. We want it to be a living lab, which basically means everyone's involved from the beginning and we're targeting user needs. So you guys are engineers. It's really important, as I talked about right at the beginning, to collaborate, right? We can't do any of this if we're developing new games without people who can program not only the hardware, but the software. So one company that we're working with is Stellar X, and they're really interesting because what they're trying to do is they've done all the background programming, and basically anyone can drag and drop and create any game in VR. That's one example of something that we're doing with a company, and lots of others. I think this is not too important. These are what we're trying to focus on, right? We want to understand, does it work? How does it transfer? We want guidelines. So right now, a therapist who wants to use VR, there's no clinical practice guidelines. There's no like, if this, then that. And oftentimes we don't have those rules in rehab because there is no recipe book, but at least you need some guiding principles. And, we need to involve students as much as possible because our physio and occupational therapy students are the ones who are going to be implementing these interventions in the future. So we're going to end the presentation with a couple of last thoughts about what's coming next. So pediatric VR headsets are really important. We're seeing some of them come out, and this idea of them being less heavy for kids. Some of the ones are really, really heavy, and better hardware, and that's where engineering comes in. More ways to customize. The next slides are going to be very text heavy. So not important. So we are integrating eye tracking technology. The latest Pico Neo 4, which is a really, really great headset, has eye tracking. Before we use the HTC Vive Eye Pro, which is no longer in production. But the Pico Neo is a wireless headset and it has the eye tracker inside of it, which is great. So for eye tracking, we can look at attention and engagement, right? Where are they looking? Are they distracted? Haptic feedback, better graphics, better headsets. We do a lot of machine learning, so that the idea is, can we have models that will, based on a person's performance, then predict what the optimal challenge level might be, right? Or so in that case, if a therapist isn't there, they can change the difficulty level based on the kid's performance. We want to integrate other things into it. And certainly what we want to integrate are these physiological measures. So we just purchased a device that integrates EEG, electroencephalography, into the headset. And so we can measure objectively brain patterns of engagement, motivation, attention in the VR task. That's never going to be commercially available, or at least not, in the next couple of years. But the idea, certainly this company's goal is that people can see kind of what their brain activity is and how much more focused or intense they are in the VR than they would be otherwise. But we're using it for research purposes. So we're going to end. We're going to start with the clinical challenge, not the technology. Too often, research sites or therapists will contact me and say, I bought the Switch. What do I do with it? It's fine, but you should be able to say, what do I need to do? And then how does the Switch answer those problems? Personalization and precision is important with AI. and we need to share our knowledge. And that's what I've got. Thank you.